Okay, we're jumping into the curvature now, which is one of my favorite topics. Actually, this one and the one after it, because we're building up to some really cool stuff here. So, okay, let's see where we're at here. If you remember, we defined t to be, which is, it's just the vector v over the norm of v, to be the unit tangent vector at any point p on some curve c, and c is going to be parameterized by some position function r. So p parametrized by some position vector r sub t. And we also said that t is the rate of change where s is this arc length parameter. Now, as the curve bends, t turns. And I'm going to jump over to GeoGebra and show how this looks in an animation. And so the curve we're looking at here is the helix, our favorite. It's cosine ti plus sine tj plus tk. And on the GeoGebra here, I graphed it from 0 to 2 pi, so you just get one turn of the helix, and we're going to see what it looks like when t moves along the curve on the points p. Okay, so it looks like I'm recording. Yes, I am. And I have I've done a bunch of work previously because it takes forever for me to type these in, but I put in the curve, which you can see here. It's just one revolution of the helix. And then I also put in, let me get rid of this. I also put in this, where the hell is it? There it is. See this little vector here? On the p, so that's the unit tangent vector. That's cap t. Make it a little bigger here. All right, there's cap t, and if I drag it along here, you see that this cap t. Oops. This cap t just follows. Damn, it's down there. To resize it. Trying to get the perfect angle here. That's not bad. So it just follows the direction of the curve. And it's always tangent to the curve. And there, that's the best one, right? And if you go from straight above, you can see how it's always tangent to the curve. And going up, it's also pointing up. So, okay. So the rate, this is key, the rate at which t turns per unit length, not time, per s. So the rate at which t turns per unit length is called the curvature. And the number measures bend, okay? So we use a Greek kappa. It's supposed to be lowercase kappa, but on paper, they all look the same. And what it is you take the derivative of t with respect to s So this says t is turning with respect to s at a rate, and we're measuring that rate by the absolute values. Right? And so if k is big, then the curvature is big and it's turning really fast. And if k is little, then it's a nice slow turn. And this is really similar to concavity. Okay. So let's get a handle on this number here. Okay. So we start off, k, it's supposed to be kappa. So kappa is defined to be the absolute value of dt ds. So the magnitude of this derivative vector. Okay. Now using the chain rule, staying inside the absolute values here, I have dt d little t. So now that's the t parameter times dt ds. I just did the chain rule on this guy. So this is going to be equal to, I'm going to pull this 1 over, and now this flips, ds dt times d cap t d little t. And it turns out that this is just the norm of v. Times dt dt. And this is the value of kappa. Okay. So kappa is defined with respect to s. It has to be because we're doing turns per unit length, and that's why I introduced the s parameter. But computationally, the s parameter is really hard to get a handle on, just by the way these things are defined, whereas t isn't. And see, this guy is all in terms of t. This is v of t, and that's dt dt. So this is all in terms of t. So now we've almost used s as a dummy variable, but it's not. It actually gives us the ability to do this computation. But this is the one you want to use when your professor asks you to compute curvature. Okay. Oops, come on, turn over. Okay. All right. So, since the norm of t is 1, it's a unit vector, and dt ds is orthogonal to t. Let's think about that for a second. Dot product equals 0. Okay. Hence, if we divide dt ds by its length, which is this kappa, we obtain a unit vector orthogonal or normal to t. And we label this new vector cap n. Okay? And here's the definition. The principal unit normal for a smooth curve C is the vector n, which is 1 over kappa times dt ds. Okay. And note that n points towards the concave side of a curve, if a curve actually has sides. So if I have some curve out here in space, this is curve C, it's parameterized by some position vector R. If I take some point here, P, and I go out and I make a nice big tangent vector, say this is unit, it's got unit length 1, right? Orthogonal to this guy going inward is the principal vector, and these guys are orthogonal. And now, if I'm as clever as I think I am, I'm going to go back to GeoGebra, go back to the helix, and make a pretty picture with the T and the N on the curve as P goes around a point. Okay, well, I did my best to get the N to show up on GeoGebra. I'll figure it out, like everything, it just takes time. But for now, just know that as this guy moves along here, if I put another T up here like that, then the N is always perpendicular to the T, and it moves along together like this. Okay. I like the animations on GeoGebra. All right, so again, this is page 2. We have N is defined as 1 over kappa times dt ds. Now there's that annoying s in there, right? We can't do computations with the s. So we're going to change this n around just like we did for t to make it all in terms of little t, and that way our computations are easier. Okay, so rewriting this, kappa is the norm of dt ds, and then over here I have dt ds, right? So I just use the definition of kappa with respect to s here, okay? And then for the fun part, we have to get the t back in there, so we're going to chain rule. So here I'm going to rewrite this 1 over the norm dt ds times the chain rule on this guy is dt d little t times dt ds. Okay. TDS. All right. Okay. And now get some color in here. So this guy just became this. And now this guy I'm going to work with. Right? And it's in the denominator. So it's kind of a mess. So, okay. So now we have, rewriting the top, we have dt d little t times dt ds all over this guy, which is dt d little t times dt ds, like this. Okay. So I've just done, oh, that's a vector. Okay, so these are just numbers. They're not vectors, so we can cancel them. And I'm left with the vector dt dt over its length. And that makes it a unit vector, orthogonal to t. Okay. And of course, you don't have to do all this, but I just want to show where it comes from, right? So now we want to find, here's our big example, the crux of this little lecture here, which hopefully comes out nice. We want to find T and N, T and N, for a circle. Just fiddling with 2 space now. This is going to be cosine 2t I plus sine 2t j. Okay. So this is just formulaic here. First we got to find v, which is minus 2 sine 2ti plus 2 cos tj. Then we have to find the norm of v, which is what? 4 sine squared 2t plus 4 cos squared 2t. And that turns out to be 2. When you factor this 4 out, you get sine squared plus cosine squared, which is 1, and the square root of 4 is 2. Now we get that. So now we want to find t, which is v over its length. And that's minus 2 sine 2ti plus 2 cos 2tj all over 2. That's nice. So it's minus sine 2ti plus cos 2tj. Those are vectors. All right, remember what n is. N is dt dt over the length of dt dt. So now we got to find dt dt, d cap t d little t. Okay. So again, we take the derivative. This is minus 2 cos, God, I can't write, cos 2ti, minus 2 cos 2ti, minus 2 sine 2tj. Okay. And not shockingly, dt dt is exactly above as that. It's 2. So now we write down n here. And n turns out to be minus cosine 2ti minus sine 2tj. Okay. And what did we say t was? I'm on a different sheet of paper, so I'm just rewriting it. T is minus sine 2ti plus cosine 2tj. All right. Let's see if these guys are actually orthogonal. If we dot t and n, what do I get? I get cosine t, cosine 2t sine 2t minus sine 2t cosine 2t, and that's 0. So they're orthogonal. That's good. Right. And let's look on the circle here. This is just a fancy parametrization of the unit circle. Okay. And let's let t be pi over 4. Okay. Right? So what's t of pi over 4? Well, first of all, let's find the point. What's r of pi over 4? R of pi over 4 is cosine pi over 2i plus sine pi over 2j. And that is here. So this is r of pi over 4. Okay. Let's find t of pi over 4. All right. So we plug that in here. We get we get minus sine pi over 2I plus cosine pi over 2j, which is minus I. Whew, that's good. So if this is I, then minus I is this way, so here it is. That's t equals minus I, so there it is. There's the tangent vector, right where it's supposed to be, going in that direction because our motion is this. And now let's find n of pi over 4. Where the hell is it? It's up here, which is minus cosine pi over 2I minus sine pi over 2j. So this becomes, I had a little moment there, minus j. Okay, that's good, because j goes this way and minus j goes that way, so there it is. And there's n. And they're orthogonal, we showed that already, and as I said before, n is always going to face into the curve, into the concavity of a curve at any point. Okay. And that is all I have. This is homework 4, section 13.4, 111, 13, and 18.